This webinar is about designing a cold form steel beam using AISI S100-16, specifically using the direct strength method for that design. As an outline here, I'm first going to give you a bit of an introduction. Then for those a little less familiar with cold form steel, talk very briefly about how cold form is unique as a material in the engineering design process. I'll then go through the meat of this presentation, which will be designing a cold form steel beam. Full process, talking about the flexural capacity, shear capacity, bearing capacity, or in cold form lingo called the web crippling capacity. Then the load interactions and deflection, which does work slightly differently for cold form versus other materials. Then give you two example beam calculations before concluding and addressing any final questions anyone has. So first about me, my name is Brooks Smith. I'm a licensed professional engineer in the United States. I have a master's degree, and I'm also a chartered professional engineer in Australia. Conveniently, Australia and the United States both have almost identical cold form codes. Currently, I'm the lead engineering developer for ClearCalcs, which is a cloud-based structural engineering design software. We are currently in the process of launching in the United States and recently added cold form steel beam and column/stud calculators to our platform. So hence we're running this webinar now. I have, prior to that, 8 years of previous experience in, most recently, research and development consulting, in which I specialized in cold form steel. Working primarily in the United States, but all over the world as well. I had research fellowship in thin-walled steel and the system behavior of that. Thin-walled steel referring primarily to cold form steel, but also to porous steels as well. That's a topic for another discussion. And my first job out of grad school was as a forensic structural engineer, where I specialized in reinforced and post-tension concrete. So this is going to be the only advertisement slide I'm going to show you about ClearCalcs. You're seeing this webinar for free, so we are going to very briefly talk about our platform. We are a cloud-based structural engineering platform that instantly calculates results for you. We're a bit more accurate than many other design software packages out there in that we have a full finite element backing to us. And because it's cloud-based, there's no licensing to worry about, and it's available anywhere, no matter where you're working from. And it's very easy to work collaboratively as a team on the same project even. So back to cold form steel. Today's goals here will be our goal is to have you leave this webinar with the ability to design a cold form steel beam according to the most recent AISI S100. I am going to make some assumptions in there so as to ensure this webinar doesn't last more than about an hour. Those include that I'm only going to be talking about C or Z sections right now, and particularly those bent about the strong axis. I'll briefly address where some of the differences occur for other types of sections and for bending about the weak axis, but I'm going to be focusing on C or Z's about the strong axis. Also going to be assuming that there are negligible holes in the cross section. In the direct strength method, you need to take some special considerations for dealing with large holes within the cross section. Generally, you're not worrying too much about that, but when you have large cutouts in the web, you may have some additional considerations to take into account. I'm going to be using the direct strength method, which is the preferred method in AISI S100. And I'm going to be assuming that all the sections are pre-qualified. Any standard section you find is going to be pre-qualified. If it's not, there are just a number of additional checks that you need to do to make sure that the direct strength method is still valid for it. I'll also only very briefly be addressing detailing. We will be distributing this slide deck as well as a video of the webinar after this. So if you would like to reference it later or pass it on to colleagues as well, we welcome you to do that. I ask that please feel free to ask any questions as I go along. I prefer to answer questions while I'm still on the topic. I do ask that you please use the Q&A feature on Zoom here. Don't use the chat or messaging feature. Q&A feature, it's just a lot easier for me to keep track of what I have and have not answered. If you do have particularly involved questions, feel free to ask those at any time, but I may save those until the end of the webinar. And just a quick note, everything I'm going to be saying today is going to be based upon the codes and AISI S100. Cold form is my area of specialty. I've done a bunch of research in it, so I do have some knowledge of likely changes that will be upcoming and things that I do and don't like about the standard, but I'm not on the committee and I'm not intending to be communicating any of those opinions in this webinar. So strictly based upon the codes. So how cold form steel is unique. Those of you already very familiar with cold form can zone out for the next couple of slides. If you aren't as familiar, cold form is particularly unique in its design because of buckling. Buckling is a very major issue. Most sections will buckle before they yield. Those of you used to hot rolled steel will be used to most of your sections being compact. In cold form, essentially most of your sections are slender. Bearing and web crippling is also a major issue in cold form. Buckling of the web at either supports or at point loads is not unlikely to control your design. So you usually have to consider bearing in most materials, but in cold form, it does actually have a reasonable chance of controlling, so you need to be careful with it. Cold form also prefers a design method that involves a finite element, or in cold form terms, finite strip analysis. However, this only needs to be done once for any given section, and often can be avoided if you really want to as well. Finally, cold form materials are very customizable. So the whole of AISI S100 is aimed at being able to work with almost any arbitrary cross-section. So specifically for buckling, again, those of you familiar with hot rolled steel will be used to the compact, non-compact, or slender classifications. And the extra calculations that AISC requires for slender beams. Many of you, even if you have worked frequently with hot rolled steel, you may have never even touched those equations or very rarely done so because virtually everything's compact. But essentially in cold form, almost everything's slender. So we have extra calculations that basically always need to be done. We consider all three buckling modes separately: local, distortional, and global, where global encompasses both lateral buckling and lateral torsional buckling. We use stiffeners in cold form to mitigate the buckling. If you've seen a C section, the little lip is a stiffener in and of itself, but you can also have fancier stiffeners, such as the little divots that you see in the photograph on the lower right there as well. Those serve to help stiffen the flange as well. Bearing and web crippling. In other materials, it's just called bearing. In cold form, we use a more specific term, web crippling. Same thing, essentially. If your web isn't directly restrained by means of, say, using a bracket for your connection at either supports or underneath point loads, then you need to check web crippling. In other materials, such as hot rolled steel, those checks exist, but they're pretty simple and they rarely control. In cold form steel, they have a decent chance of actually controlling your design, and they're highly dependent upon the precise cross-section and the arrangement of forces in your beam. Keep talking about finite element analysis. We're more likely to use a slight variant of that called finite strip analysis in cold form steel, but this is a preferred method in AISI S100. When you use a direct strength method, you're required to use a rational analysis. Usually that will take the form of the finite strip method. Sometimes there are other analytical methods you could potentially use, but usually it's a finite strip method you're going to use. Generally, it only needs to be done once for a section, and there are ways to avoid it using some of the appendices in AISI S100, but we prefer generally to use finite strip method. And I'll talk in more detail about it later in this webinar. Again, highly customizable shapes. Most shapes you see are going to be based upon either SFIA or SSMA standard sections. That's the Steel Framing Industry Alliance or the Steel Stud Manufacturers Association. They have a list of about 700 or so sections that they've standardized and manufacturers will generally all produce. Those are very available, can probably solve most of your needs, but custom sections are also very possible in cold form steel and can sometimes even be quite economical. Probably not things quite as weird looking as what you see in the lower right there, but custom sections nonetheless can be quite economical in cold form steel. So now moving on to the meat of this presentation, and I'll talk about how to design a cold form steel beam. I'm going to go through all of the design steps of that: flexural capacity, shear capacity, bearing capacity, load interactions, that's flexural and shear interaction, flexural and bearing interaction, as well as deflection. And then after that, go through some examples. So your first step in designing a cold form steel beam is to calculate all of your demands using either AISI 7 or the International Building Code, IBC, whichever you're using in your design. I'm not going to go through the details of that. That'll be a topic for another webinar, but hopefully you may already be aware of exactly how to do that. The limit states then that need to be checked for and capacities that need to be calculated in cold form steel beam, however, include the flexural, shear, web crippling, load interactions, and deflections. Before you can really start any of these calculations, you need to make sure you have a number of your geometric values. If you're using a standard section, these will all be given by your manufacturer. If you're using a platform such as ClearCalcs, this will likely already be in the database for any section that you want. But you need your moments of inertias, your gross cross-sectional areas. The location of the shear center is very important in cold form. So x naught is the distance from the centroid to the shear center. Radii of gyration, about both your principal axes as well as the polar radius of gyration. St. Venant's torsion constant and torsional warping constant. All of that you need. I'm not going to go through how to derive those. If necessary, if you're using a very custom section, you probably want to use some program to help you derive all of these. So first step is your flexural capacity. And I mentioned we're going to calculate all of the different types of buckling separately. You start with global buckling. Yielding and global buckling are essentially considered together in one equation. MNE is your overall global buckling capacity, and that's equal to the lesser of SFFN or SFY-FY. Now, SF and SFY are both elastic moduli. Usually they're going to be the same thing, but they are different variables for a reason. SF is your elastic modulus relative to your elastic bending modulus relative to the extreme compression fiber. SFY is relative to the first yield fiber. Usually those are going to be the same thing. If you have a symmetric section, such as a C or a Z section, bent about its strong axis, they're going to be exactly the same thing. Where it could differ is, for example, when you have a C section bent about its weak axis, where you may have, for example, a tension yield occur before your first compression yield in the cross section. You can generally use just SFY as a conservative value, but to be more accurate and to get a little more capacity, you should calculate each of these separately if applicable. Again, in our case, they're exactly the same thing. FN is where global buckling is considered, and it depends upon an FCRE value that I'm going to talk about in the next slide. FN may alternatively be determined directly using finite strip analysis, or using the effective width method, which is in the appendix of AISI. We're going to use an analytical method, which is usually what you're going to prefer to use. And for that, you're going to end up with that Fn value equal to either the yield stress, your critical buckling stress, or something in between, depending upon how likely global buckling is essentially going to be. So what's FCRE? That's your main global buckling parameter. Its value depends upon what section you're using. I've copied here the equations for C sections and Z sections. There are other equations for other types of sections, and if you have a truly arbitrary section, you're going to need to use an external analysis to determine what FCRE will be. But C or Z sections, it's relatively straightforward. You'll notice that the equation for a Z section is exactly half of that for a C section. And the values you haven't seen in there before are CB, sigma, and the two sigma values here. CB, you may have seen in other material designs. That is accounting for the pattern of the moment along the length of your beam span, each individual span. For that, you have your moments at your quarter points and consider the ratio in there. Alternatively, if you don't know what those values are, you can conservatively take CB as 1 in all cases. For cantilevers, you have to take it as 1. So those sigma values then are the buckling stresses in lateral buckling, that's sigma EY, and in torsional buckling, that's sigma T. These equations you may recognize as looking sort of like an Euler buckling equation, but considering the radius of gyration. Ly and the Lt and the sigma T equation are your unbraced lengths, and Ky and Kt usually is going to be equal to 1. That's essentially if your restraints are pinned, which they will be in most cases. If you have fancier types of restraints for lateral and torsional bracing, then K may equal something else, but usually they're going to be 1. So calculate sigma EY, sigma T, and then plug all that in, get FCRE. Go back to this equation to find Fn, plug that all in. You end up with your global buckling capacity of MNE. There is an additional thing, however, for global buckling, and that's in cold form. We will allow you to take a little bit more capacity in most cases, if called the Inelastic Reserve capacity. Essentially, that's allowing small amounts of localized yielding as long as it doesn't affect the stability of the beam. This is an optional provision. There are certain types of connections, particularly welds, that may forbid have it taking into account that inelastic reserve capacity, but usually you can. Usually you can take it into account. It is only allowed if MCRE is greater than 2.78 MY. So just do that check first. That's essentially saying that global buckling is unlikely to happen before yield. So we can use some of the inelastic reserve capacity that's available in there. If you are using that inelastic reserve capacity, then your MNE becomes equal to this equation here. The only variable here that will be unfamiliar is MP. That's your member plastic moment. It's equal to Z times Fy. Unfortunately, that value is generally not given in manufacturer's information. I've only seen it once or twice actually given by manufacturers. However, it's relatively straightforward to calculate, at least for symmetric sections. That's where you set your compression area equal to your tension area and calculate the moment capacity where everything is yielded. So finite strip and finite strip analysis. This will be necessary for calculating your local and distortional buckling capacities. the MCRL and MCRD that are equivalent to the MCRE that you used earlier. Most easily, you're going to determine those critical buckling capacities using that finite strip method. And there are two main programs that I'll point to. There are others available as well, but two ones that I'll point to here. CUFSM is available for free, produced by Johns Hopkins University. And Thinwall, which is produced by the University of Sydney in Australia. That does cost money for commercial use, but both of these will do finite strip analysis for you. The critical capacities you're going to calculate for local and distortional buckling are generally going to be valid anytime you use a given section. They generally do not depend on length. The only time they will is if you have a very, very short beam or if you manage to restrain your local and distortional buckling at very tight intervals. But generally, as long as your beam is longer than about 24 to 30 inches, and I'll talk more about exactly what that means in a second, then these capacities will be able to be used for any time you use the given section. So these are somewhat scary looking plots potentially, but and I will leave you to go through the references and tutorials for the preferred program that you decide to use for a direct strength method analysis or finite strip analysis. But basically, I wanted to talk about the basic results so you get a feel for what's going on here. When you do finite strip analysis, you will end up with a plot that looks something like what's in the lower right here, where the x-axis is the half wavelength and the y-axis is a load factor. Local buckling occurs at a smaller half wavelength than distortional buckling, which also occurs at a smaller half wavelength than global buckling. Now, what exactly does that mean? In global buckling, you have a longer length over which your bending is occurring than you would for local buckling. So using just a basic kitchen sponge as an example here, global buckling is what happens here when I'm just bending it overall. You'll see that the half wavelength is equal to the full length of my sponge here. If you restrain that global buckling, however, and you bend it, you'll see little divots of curving happening in the middle. That's a much smaller half wavelength. That's your bending that's occurring over a much smaller length. So essentially, finite strip analysis is doing that type of analysis, seeing over every possible half wavelength what is going to be the likelihood of divots bending forming. So usually you're going to have two local minima show up in these plots. The first one at the lower half wavelength is going to represent your critical local buckling capacity, and the second one is going to represent your critical distortional buckling capacity. If you wanted to use finite strip analysis for global buckling, you could as well. However, that's going to be dependent upon length. You're going to pick out the global buckling capacity at the length of your beam. But usually, you're just going to use this for local and distortional buckling and take those two local minima. Those are going to be equal to your MCRL and MCRD. But once you have those MCRL, MCRD values, you still need to do a little math on them. So for local buckling, starting out with that, this involves, in cold form terms, the cross-section staying still, except for the webs, the flat web and flange, the flat portions of the cross-section. Those may bend outwards. So essentially the corners of your C-section, as an example in the lower right here, will stay in the same place, but the web or the flange will bend a bit. That's local buckling. The calculations in AISI S100 are technically considering the interaction of local buckling with global buckling as well. Usually local buckling occurs with a half wavelength of 4 to 10 inches. And your slenderness coefficient is what you start out with. That's your lambda L value here, square root of MNE, your global buckling capacity, divided by MCRL. Once you have that lambda L, you just pick one of these two equations as appropriate and calculate your total local buckling capacity, MNL. There is also inelastic reserve capacity that's also relevant for local buckling. That is allowed as long as that lambda L value is less than 0.776. In other words, that local buckling is likely to occur after yielding, and if your global buckling is greater than MY. The calculation for inelastic reserve depends upon whether your first yield is going to occur in tension or compression. So if your first yield is in compression, or if they're theoretically simultaneous, such as for all the sections I'm talking about when it's symmetric, then you use a first equation here, where MNL equals this function of MY, MP, and CYL. Plug into that, you'll get your local buckling capacity. If your first yield is in tension, you have a very similar equation, but you take the minimum of that and MYT3. MYT3 is essentially taking the same thing, but CYT equals 3 and using your SF instead of SFY in the calculation. So MYC versus MY in that. Distortional buckling involves movement of the corners of the cross section. However, where not all corners are moving together. If all the corners are moving together, that's global buckling. If different corners are moving relative to each other, such as in lower right here, if the flange bends down and everything else stays basically the same, then that's distortional buckling. We don't consider any interactions with other types of buckling in this. And distortional buckling usually occurs with a half wavelength of about 16 to 30 inches or so. Similar to local buckling, you calculate a slenderness factor first. That's your lambda D here. You notice it's MY instead of MNE because we are not considering interaction with global. And again, depending upon the value of that lambda, you switch between one of these two equations that you plug into to get your distortional buckling capacity. And again, distortional buckling also has an inelastic reserve that you can consider. Can be considered based upon whether your lambda is less than 0.673, or that is if distortional buckling is likely to happen only after yielding. And again, the calculation depends upon the nature of the first yield, whether it's in compression or tension. These equations will actually look very similar to what you already saw in local buckling. So overall, your overall flexural capacity, now that you've gone through all that work and number of slides here, you can finally calculate what your flexural capacity is for the beam. That's simply equal to 0.9 times the minimum of MNL, MND, and MNE, your local, distortional, and global buckling capacities. As a side note here, AISI S100 relists phi B equals 0.9 in every single clause. It's always equal to 0.9 in Flexure. So I'm giving you just a simpler form of this equation. It's just 0.9 times the minimum, whatever. Now, shear capacity. Shear actually takes a somewhat similar form to the flexural calculations, but it's all analytical. There's no finite strep involved in it. It's based upon the area of the flat portion of the web. So that means excluding the radii of the corner of the cross section. So it's only the flat portion of the web. And for that, first you calculate a critical shear buckling capacity, VCR. That's comparable to the MCRL, MCRD, MCRE that we looked at earlier, but it's calculated purely analytically. That's equal to the area of the web times this calculated buckling capacity that you see in the middle of the slide here. Of note, for some reason, AISI prefers to use mu instead of nu. That's still Poisson's ratio. It's still equal to 0.3 for steel. If you have an unreinforced web, if you don't have stiffeners used to reinforce your shear, then KV is equal to 5.34. If you have a reinforced web, then it's equal to one of the two equations here, depending upon the ratio of the length to the width of the shear panel that you've produced with your shear stiffeners. This is, by the way, a difference that was introduced with supplement 1 in AISI S100-16. This used to just be one equation. It's been split into two now, depending upon the ratio of length to width. So if you haven't updated your specification to supplement 1, that's a difference that you'll see in supplement 1. So once you have that critical buckling capacity, you will split out into different calculations depending on whether you have stiffeners or not. So without stiffeners, you first calculate the shear yield force equal to 0.6 times AW times Fy, and calculating a slenderness coefficient for the shear buckling as well. And then you switch based upon that slenderness coefficient as to whether you take your overall shear capacity equal to the yield capacity, the critical buckling capacity, or something in between. The value for shear is 0.95. So your overall shear capacity is then going to end up being 0.95 times Vn. With stiffeners, this assumes that you have minimum shear web stiffeners with spacing not exceeding twice the web depth. If you don't meet that, then you essentially consider it to be without stiffeners. But assuming you meet that, then you use the following equations for calculation with shear stiffeners. Those of you a bit more eagle-eyed here will notice that these equations are essentially identical to what you already saw for flexural local buckling. We're checking for local buckling that may occur between the stiffeners in shear. So first calculate the yield force, slenderness coefficient, and then switch based upon the slenderness coefficient. Again, phi value is still 0.95, and your overall shear capacity is 0.95 times Vn. Now, web crippling capacity, I talked about how that is quite important in cold form steel. It is all based on just one single equation. That's the equation that I reproduced at the top of the slide here. This accounts for effects of the angle of the web, which is usually going to be 90 degrees, but not always for more custom sections. But in all of our cases, it's 90 degrees. Quarter radius, how tightly you bend your cold form section in the roller. The bearing length, and the web height slenderness. So that's your theta, r, n, and h values respectively. The key to this equation is in all of those C coefficients. C at the start and then CR, CN, CH. There are tables for looking up what those values should be for C sections, Z sections, built up I sections, hats, and steel decks. And if you have some other type of section, you're going to need to do a fancier analysis. Of note, that equation and the tables are to be done per web. So for box sections, for nested Z sections, or anything that has more than one web, you're going to multiply that equation by the appropriate number of webs. So for a nested Z section, multiply the equation by 2. Phi W, the phi factor for web crippling, is not constant. It's also looked up in the tables. So what do those tables look like? Here's an example for the C sections. You have 4 things you need to look at when you are looking up in this, in this table. The support and flange conditions. First, whether it's fastened to the support or not fastened to the support, that's screwed or bolted into the supports. Whether your flanges are stiffened or not. So generally whether there's a lip on your section or not. And whether you have 1 flange loading or 2 flange loading, and whether it's an end or an interior condition. So what do 1 flange and 2 flange loading mean? Essentially, that is whether you have loads on the top and bottom of your beam at the same time within a certain distance. So you have 2 flange loading if you have concentrated loads on the bottom and the top of your beam at the same time with a spacing of less than 1.5 times the height of the beam. That would be 2 flange loading. Anything else is 1 flange loading. And then end versus interior, usually an end location is anything that is less than 1.5 times the height away from the end of the beam. And a interior location is anything greater than 1.5 times the height. So you take all that information, you look up the appropriate row in this table, find your C, CR, CN, CH values, as well as your phi value, then plug those in through your equation. You'll notice that there is an additional column here for limits. These equations are empirically derived, these coefficients are empirically derived. So if you exceed that limit, then the coefficients may not be valid anymore. You should consider a more advanced analysis. But any standard section you find will be within those limits, or should be anyway. You have a similar equation for Z's, similar table for Z's. And again, you look up whether it's fastened or unfastened, stiffened or unstiffened, 1 flange or 2 flange loading, and end or interior. Of note, there are cases that have not been tested and don't exist in the table. So for example, if you have a beam that's fastened to the support but with unstiffened flanges, you'll notice that you have no values in this table for that. Usually what we'll do in that case is use the more conservative option. So even though it's fastened, we'll use the unfastened value, unstiffened flanges, and look up using that. Then load interactions. We have interactions we consider between flexure and shear, as well as between flexure and web crippling. Interaction between flexure and shear, the calculation, which equation you use, depends upon whether there are shear stiffeners present or not. Without shear stiffeners, it's a square root sum of squares equation. The VA is equal to your factored shear capacity, that's phi times Vn. MALO is a slightly different equation. Theoretically, it's equal to MNL, but without considering global buckling. So what does that exactly mean? It means the codes will give you a number of parameters to substitute in. I'll just give you what the actual equations work out to. So MALO is equal to phi times MNLO, and you're going to calculate your local buckling slenderness coefficient using My instead of Mne. So it's equal to square root of My over MCRL. And then you switch based on the slenderness coefficient. And MNLO is equal to either My or a function of My. There is no Mne considered in these equations. Additionally, if there are web stiffeners, you also consider you take MALO equal to the minimum of that MNLO you just calculated and MND that you had previously calculated. Flexure and web crippling. This applies for both concentrated loads at supports and at point loads. So at negative moment or usually positive moment locations as well. There is a specific phi value for this interaction equation, and you do not consider the phi values for web crippling and flexure at all individually. So for an unreinforced single web, you use this first equation. I'll take note here that it's the denominators are Pn and MNLO. Those are equal to PA and MALO, but without the phi factors. So plug into that equation and compare with the limit set there. There is an exception for this that exists for members where the webs are spaced less than 10 inches on center and have lateral bracing, such as that shown in the image on the right there. Other options are considered specifically for either back-to-back C-sections or nested Z-sections. If you have difficulties with your web crippling capacity, it's common to double up your C-section or Z-section by means of either putting your C-sections back-to-back or nesting your Z-sections. And those have slightly different equations that you're considering in there. Deflection, I mentioned, is slightly different for cold form steel. There's an important difference between the effective and the gross moments of inertia. Conservatively, you can always use the I effective values that are given by manufacturers in their literature. Most accurately, there are some long equations that you can make use of in the cold form steel design manual. But more practically, what you are probably going to want to use is the only slightly more conservative equation given here. And that is taking your gross moment of inertia and ratioing it by the capacity divided by the demand. So M is the moment demand due to service loads that you're considering at a maximum of the yield moment. So for example, that might be your D plus L. And then MD is equal to the same thing as MN that you had calculated earlier for your flexural capacity, except that MN should be recalculated, replacing all instances of MY with M. So essentially, you're recalculating flexural capacity at service loads, assuming service loads are your maximum. So the manufacturer's I effective values, generally you'll see them as actually equal to this equation, but where they'll set M equal to the maximum reasonable dead load plus live load. So yeah, you use your I effective value in calculating deflections in cold form steel. Also of note, cold form steel will usually assume has a elastic modulus of 29,500 KSI. We get a little bit of an added boost in stiffness because of the cold working that occurs in cold form steel. So now wrapping it up on beams, this represents everything that I've talked about here, the general requirements for cold form steel beams. There are some alternative equations which can generally give you a little bit more capacity for very specific types of systems. So if you have a beam with one flange through fastened to a deck or one flange through fastened to a standing seam roof, then you can generally make use of some slightly less conservative equations given in section I of AISI. I'm not going to go through the details of those. They're actually relatively straightforward equations, but you can make use of those to potentially get a little more capacity. If you have steel racks, that's governed by some of the more mechanical engineering equations in an ANSI standard. And if you have a diaphragm system, there are some alternate AISI standards that you can make use of for those. S310 for a deck diaphragm, S240 for a flat sheet diaphragm, and S400 for specifically seismic circumstances. So now going on to some example calculations. Our first example will be a simply supported beam, as shown here. We're going to use a 362 S137-54 section. That's how you're usually going to see a cold form steel section written out. The first three numbers, 3.362, means a web height of 3.625 inches. The S refers to a C section. You'll also see a Z for a Z section, a U for an unreinforced C section, or an unstiffened C section, excuse me, or a T for track section. The next three numbers, 137, refers to the flange width. That's 1.375 inches in this case. And the dash 54 refers to the thickness. So 54 mils is your thickness, or nominal thickness anyway. Many sections may be available in both 33 KSI and 50 KSI strengths. Custom manufacturers can also potentially do other strengths as well, but 33 and 50 are the ones that you will see frequently. And because sections may have multiple standard yield strengths available, you'll often see the yield strength listed along with the section name as well. So we're going to assume a simply supported beam in an office building with a dead load of 15 PSF, live load of 40 PSF, 7 feet 2 inches long, that's 86 inches. We're going to assume a 16-inch on-center spacing for our purlins, so 16-inch tributary width. We'll assume no transverse shear reinforcement for now, and assume that we have lateral bracing at 24 inches on center, and no additional torsional bracing. So I'm going to go into ClearCalcs to show the example as to how this works here. Show how you go through these equations. So logging into ClearCalcs at clearcalcs.com. I'll create a new project. Just call it webinar for now. Project number, client name, and whatnot are optional. And then I'll add a new calculation. We offer a number of different types of calculations, timber, steel, cold form. I'll select cold form steel beam. And you'll see all of the calculations open up here and calculated live. So I said this was a 362 S137 -54 at 33 KSI section, 86 inches long, with 24-inch on center lateral spacing or lateral bracing. And 15 PSF dead load, 40 PSF live load. We're going to assume that occurs over the full length of the beam. That will all get calculated out here, and you can see that our most limiting factor is deflection here, where we're at 82% of our limit. We set our limit to L over 360. Other capacities are listed here. Our negative moment demand is 0 because this is simply supported beam. And you'll see the shear, the web crippling, and combined bending and shear, combined bending and web crippling values. All the calculations are done below here with all of our load combination analysis, checking every possible load combination listed in AISI 7 in this case. Unfactored loads, we only have dead and live loads, so everything else is 0 in here. And within these calculations, we're going through and calculating out for you what the yield moment capacity, plastic moment capacity, global buckling. You can turn on and off inelastic reserve capacity. Though this section is unable to make use of it because it buckles before it yields. Local buckling calculations, distortional buckling calculations, shear capacity, web crippling. Web crippling we're going to calculate for you for each individual support, and you will need to do that as well. It has to be calculated because it depends upon bearing length and location of your support. It needs to be done individually for each support, and hence you'll see in the 2 rows up at the top here for where we specify our support locations. And then combined bending and shear and combined bending and web crippling. We will allow you to also look and see what all of the equations are used in this. So for example, the yield shear force is equal to 0.6 times AW times Fy. And the exact equation reference, G2.1-5 in AISI S100. So go through all that calculation, and you end up with shear, bending, and deflection envelopes as shown there. Load diagram looks similar to what you saw in my sketch in the slide as well. And again, section works. So then going back to a second example with a more complex beam. And this beam has 3 different supports and a cantilever on one end as well. We're going to assume the same level of loading, so we're not focusing on that as a detail here. Spacing between the first section, the first 2 supports of 72 inches, between the second set of supports of 120 inches, and that leaves us with a 24-inch cantilever. We'll end up needing to use a larger cross-section here. We're going to use an S1-16, so it has a slightly longer flange width of 1.625 inches, and a 68 mil thickness at 50 KSI to make this one work. But I will plug that in and demonstrate exactly how that can work. So to make life a little easier, since our loading and such is the same, I'm just going to duplicate the existing sheet that I had just created. The overall length of my beam is 196 inches. Alternatively, you can also enter that in using formulae. So it equals 12 times 16. Sorry, 196 is my length, not 192. We have restraints for torsional bracing. We assumed at 48 inches, and for lateral bracing and positive at 48 inches. So modify those values. And then our first support we said was at 72 inches. Second support at 192 inches. That's 120 plus 72. And then that leaves us with a little bit of a cantilever on the end as well. Sorry, I did my math slightly wrong there. It's 210 inches is my total length. Give us our cantilever on the end. And I'll assume bearing lengths of 1.5 inches for everything as well. So that ends up with shear, bending moment, and deflection diagrams as shown here for our envelopes. We can see this looks pretty similar to, again, the diagram on the other page. I have not changed the section yet, so you can see that the old section, the S137-54, does not work here. We can quickly see what sections do and do not work in a member selector that will open up here. This shows what does and does not work and how every section fails. So I'm going to specifically go to a 362 S100-16. So I'll open up that one at 33 KSI first. And you'll see in this case that web crippling and bending moment actually governs here and prevents the 33 KSI beam from working. So this is why you'll sometimes have sections that exist in both 33 KSI and 50 KSI strengths. And this is an example too of web crippling actually governing our design here. But if we just bump that up to a 50 KSI yield strength instead, now that will work. And you'll see that MP value drop down to 82%. Still our governing strength, but now the calculation works. And now we're within capacity. So those are our two examples that, to quickly go through there. Now going back to presentation, I'm just going to quickly conclude here. So summing everything up, cold form steel engineering design is unique because of buckling being much more likely to happen, web crippling being much more likely to govern your design, a likely need for finite strip analysis, highly customizable shapes. In all of our design checks, we went through the full process there of global buckling, finite strip method analysis, local buckling, and distortional buckling calculations. Shear calculations, we calculated the shear yield, we calculated shear buckling, and we went through two different processes, whether or not we had stiffeners. For bearing, known as web crippling in cold form lingo, we basically just look up the values in those giant tables, plug in the coefficients, make sure we get the appropriate phi-w value for end and interior and 1 and 2 flange loading conditions. And we do that for each individual support and each individual point load. And we check load interaction for flexure and shear, and flexure and web crippling as well. Deflection, we calculate out the effective second moment of area, also known as the effective moment of inertia, and take that as consideration. We performed examples with simply supported and complex beams. So at this point, if anyone has any further questions, please feel free to ask them. Do again ask that you please use the Q&A feature rather than the messaging or chat features. We do encourage you to watch out for future webinars as well. Now that we've launched ClearCalcs in the United States, we will be holding more of these webinars for United States-based designs, with upcoming webinars on hot rolled steel, on timber, on concrete. So keep an eye out for those, and we'll run those, and they'll be free as well. So have a question of, can ClearCalcs be customized to include custom section property databases? That's a soon upcoming feature. Right now, we only have the standard sections in our database. We're very happy to add any sections that you would like added. It's a quick process for us, but we do not yet have an interface for allowing you to add the custom sections on your own. Again, that is going to be a feature coming soon. And yeah, right now our United States calculations include timber, steel, and cold form steel. Concrete is currently in the works. And we will also have connections, footings, and post and sleeper retaining walls coming very soon as well, along with other types of foundations and retaining walls coming into the US calculations in the coming months. We do offer international calculations as well. Our Australian calculations are a little bit more complete, as we did start as a company in Australia. We also have Eurocode calculations that have recently been added for timber and steel as well, and concrete is in the works on Eurocodes as well. All right. Well, if anyone has any other questions, please feel free to ask them now. Otherwise, thank you for your time, and I hope this webinar was helpful to everyone.